So now we'll discuss variation of parameters. This is another method to solve a second order, a higher order, linear non-homogeneous differential equation with constant coefficients. So far we have discussed the D operator method. So the D operator. We have discussed the D operator method in which we have solved the second order linear non-homogeneous differential equation of the form a2y double dash plus a1y dash plus a naught y is equal to f of x, where f of x might be, number one, it is an exponential function, or it could be polynomial, or it could be sine alpha x or cos alpha x, or it could be something polynomial something, and e raised to power alpha x raised to the power n, the product of two function, and the fifth one e alpha x cos beta x or e alpha x sine beta x. So f of x could be an exponential function of the polynomials, or trigonometric function, the product of a polynomial with the exponential function, or product of trigonometric with the exponential function. We have discussed these 5 cases using D operator method. This is the differential equation we were solving by using D operator method, where f of x could be anything like this, or it may be a couple of more functions like this. It may be exponential function or the polynomial, they are adding together, something like that. Today we discuss variation of parameter. Variation of parameter. So for the variation of parameter, we'll have an example, and through the example we'll find how to find the solution of non-homogeneous linear differential equation using variation of parameter. Solve the following differential equation using variation of parameter. Parameters. So let me have a very simple example. 3y dash plus 2y is equal to 6. So this is again a non-homogeneous differential equation with constant coefficient. These coefficients, this is 1, this is minus 3, this is 2, constant coefficient, and this is non-homogeneous because of this function present. Because of 6, this is non-homogeneous. So how to find solution using variation of parameter? So for complementary function, by C, we are writing the D operator form, which is minus 3D plus 2 operate on y equal to 0. Then we are writing the auxiliary equation. Auxiliary equation, which is r square minus 3r plus 2 equal to 0. Quadratic, breaking up the middle term. This is r minus 2, r minus 1 equal to 0. So this is r is equal to 2 or r is equal to 1. Since the roots are real and distinct, the solution will be a e2x plus b ex. This is the solution. Now we are defining couple of functions, this and this. Let me define u1 as e2x and u2 is ex. So you can have this as u2, you can have this as u1. Then you are defining their derivatives. This is 2e2x and you are taking the derivative of u2 prime, which is ex. Now you have defined Wronskian. Wronskian after the name of mathematician. So Wronskian could be, this is u1, determinant of u2, u1 prime, u2 prime, and this must be non-zero because this solution which we have in YC, this function and this function, this must be linearly independent. For the linearly independent, I mean, if you are dividing two functions, let me have one function is there and one function is there. If I am not getting a constant, then these functions are linearly independent. If I am dividing and I will get a constant, it means they are proportional to each other. So they must be linearly independent. They must be linearly. If they are linearly independent, then the determinant of 2 by 2 matrix must be non-zero. Because if they are proportional to one another, so the derivative must be proportional to one another. So if two rows are identical, then the value of the determinant is 0. So let me have whatever I have taken the function. This is ex, this is 2e2x, and this is ex, their derivative, and I am solving determinant of 2 by 2. I will multiply this by this. So since bases are same, powers are added, and then put a negative sign, I will multiply these two. 2 ones are 2, and bases are same, powers are added. So this is minus e3x, which is non-zero. Variation of parameter, the Wronskian must be non-zero. So define two new variables. V1, which is integral minus u2 f of x over Wronskian dx. So this is a new variable you are defining like this. You have u2 with you have fx with you, and the Wronskian with you. So putting the values, let me take minus outside. u2 is my ex, f of x is 6, because this is your f of x. This is your f of x, 6. And the Wronskian I had minus e3x dx. This is the Wronskian. So let me solve. This minus goes, and I will 6 taken out, and this is ex and e minus 3x dx. Because if I am taking this to the numerator, the exponent is, the power is negative. So I am going to add them, minus 2x dx. Let me integrate, minus 2 e minus 2x plus c1. So this becomes e minus 2x plus c1. Do not forget to put a constant of integration here, which is c1 or anything you wish. But you must have c1, because here we have a and b. v2 is u1 f of x over Wronskian dx, putting the value. And u1 is this time is this, which is e2x, and f of x is 6, and Wronskian is e minus 3x dx. This is the Wronskian you are having. So this is minus 6 is taken out, and this become minus, this is, sorry, 3x. Wronskian is 3x plus 3x. Minus 6 is minus x dx. Because I am taking this to numerator with negative, and bases are same, powers are added. Like this, I am integrating now. 6e minus x plus c2. This is my v2. So I have v1 is this, and I have v2 is this. The general solution is y is equal to u1 v1 plus u2 v2. This is the general solution. You have everything with you, u1, u2, v1, v2, putting the value. u1 is e2x. v1 is minus 3 e minus 2x plus c1. u2 is ex, and v2 is this. This is v2. 6e minus x plus c2. That is all about the solution. And do not get confused. It contains yc in it. Because if you are going to simplify, you will see c1e2x plus c2ex. This is yc you are having. And the rest of the thing is yp. But in variation of parameter, this is the way you are writing down the solution. u1 v1, u2 v2. So where u's are, you have taken the complementary functions, a complementary solution. The functions are u1, u2, you can take any one of them, and then v1, v2 you have to define by defining the Wronskian and something like that. So this is the entire solution using variation of parameters. Let me have another example to solve the differential equation using variation of parameters. So example again, solve. Another example, y double dash plus y is tangent x. So this is non-homogeneous because of this function. Again, a second order, the solution will be for yc, the complementary function. We are writing the homogeneous differential equation, the d operator form, d square plus 1 operate on y equal to 0. Because this d operator means operator is operating on some functions. That's why this function is taken out. This is the operator. So auxiliary equation, r square plus 1 equal to 0 and r is equal to plus minus iota. So the roots are complex. yc can be written a cos x plus b sin x. Because if I am telling you, if the roots are of the form alpha plus minus iota beta, suppose complex number always occur in pairs. So if this is the situation of a root 1 plus iota, 1 plus something like that, the solution can be written e alpha x a cos beta x plus b sin beta x. This is the situation. Now here my alpha is 0. Alpha is 0 and beta is 1. So this is the way I have written down the solution. If suppose something it is 2 plus minus 3 iota. If this is the situation, then I have to write down e2x a cos 3x plus b sin 3x. So this is all about the way I have written down the solution, where beta is 1 and alpha is 0. This is the solution. Now since we are using the variation of parameter, again let me define u1 is cos x, u2 is sin x, and the derivative u1 prime is minus sin x, u2 prime is cos x. And these functions, look, this and this, if you are dividing these two, you are not getting a constant. It means they are linearly independent. They are linearly independent. So Wronskian can be u1, u2, u1 prime, u2 prime. If you are putting the values, this is cos x, this is sin x, this is minus sin x, this is cos x, the derivative. And you will see if you are multiplying this cos square and cos square x, put a minus sign and this minus, make it plus. This is sin square x, and which is the trigonometric identity 1. So the Wronskian is 1, which is non-zero. Now v1 is minus u2 f of x over Wronskian dx. The derivation of this formula is available. So you can see from the literature, or we'll discuss later how you are going to get this. So that minus is taken out, u2 is sin x this time. Let me have sin x and f of x. F of x is this one, tangent x. So let me write f of x is tangent x, and Wronskian is 1 dx. So the formula is going to be used like this, the u2, whichever you are going to tell, whether it is a cos x or sin x. So let me solve this v1. v1 is, minus is outside, this is sin x, and tangent can be written sin x over cos x dx, which can be written sin square x over cos x dx. Sin square x can be written 1 minus cos square x over cos x dx, which can be written minus integral 1 over cos x dx and minus plus integral cos x dx. I multiply this and I have to divide. So this becomes secant x dx and this is cos x dx. And might be you are knowing the integration of this, which is natural log secant x plus tan x. This is the integration of this. And integral of cos is sin x plus c1. So this is your b1. So you have to have a constant there, which is c1. Similarly, we are finding v2. v2 is integral u1 f of x over Wronskian dx. Putting the values, u1 is cos x, f of x is tan x over Wronskian, which is 1. Tan x can be written sine over cos and cos cancelled. So you are written with, sin x. You have sin x dx. Integral of sine is minus cos x plus c2. Tangent x can be written sin x over cos x and 1 cos x is cancelled with it. So you are left with this. The general solution will be y is equal to u1 v1 plus u2 v2. Putting the values. You have u1, you have a big v1 there. Look, this is your v1 and you have u1 is cos x and v1 is such a big secant x plus tan x. Let me write in absolute value because there is a natural log there. Plus sin x plus c1. Let me close the bracket. This is u1 and this is a big v1 there. Look, this is v1 plus u2. u2 is my sin x and v2 is this one minus cos x plus c2. That's all for the question we have solved, in which this cos x when multiplied with c1 cos x plus c2 sin x. So this is the complementary function, which is the yc we have. So in the general solution, it is going to be yc, yp, everything is there. So this is going to be the general solution for the non-homogeneous second order differential equation using variation of parameter. But if there is a third order differential equation, you will get 3, u1, u2, u3. There were 3 functions and then you have to define the determinant of 3 by 3 matrix and solve the way you are solving the 3 by 3 matrix and something like that. I hope you understand the variation of parameter method to solve a second order linear non-homogeneous differential equation. Now I am writing couple of follow-ups, which is your homework. You have to solve. Using variation of parameter, solve the following. And y1 is e and y prime 1 is 0. So these are the questions which you have solved using variation of parameter. This is your f of x. This is your f of x, something like that. The last question is the initial value problem, where the function and its derivative are evaluated at a particular point. Look, this is your independent variable which is x. And if you have observed this function f of x, if I am writing this f of x so that it could be written f1 over x ex. Now, independent variable is this time taken x1. So it means this f of x is defined at the initial point. So initial point is that point in which the functions, this one, the one, these are polynomials and this should be defined. If I am taking, for example, the last question, if you are looking, f of x is x raised to power minus 1 ex. And my conditions are y0 is e and y prime 0 is 1. So these conditions are invalid because this is independent variable x and f of x is this. So this function is undefined at the initial point. It means at the initial point your function must be defined. So that's why this initial point is 1 this time, 1. So if you are putting x equal to 1, that's okay, this function is defined. So you have to solve the initial value problem by looking at the initial condition, whether at the initial condition your function is defined, yes or no.